Hi everybody, this is the Polynomial Summative Walkthru for people that are afraid of factoring. You shouldn't be afraid of factoring, but if you are, you can still do pretty well in this test. You can still get all the same answers, you just have to use your graphing calculator way more. So, when I graph this polynomial, hold on, let me, problem number one, I'm going to make the lower bound a little lower so I can see the bottom of it. This is a polynomial that has that characteristic W shape, fourth degree polynomial, and I'm seeing two crossing points, but the problem is they don't cross at like tick marks, so these are not going to have, I don't see integer solutions here, and I'm only seeing two solutions. I can make my calculator find those solutions by asking it for what the zeros are, and that decimal, what is that decimal? It's one of those numbers over here in the box. I've circled it. But if you don't recognize that number, you can go into your calculator and just ask your calculator, what is that 2.236 number? If you square it, you'll see that the square of the solution is 5. So we're basically talking about the square root of 5. The square root of 5 is 2.236. So the square root of 5 is one of my solutions. So if I'm right about that, then I'm going to put square root of 5 in the box and do synthetic division on the polynomial. Now, don't forget to put zeros in as placeholders where there are no terms listed. So like the linear and the cubic term are missing. All right, synthetic division, you bring the 1 down times the number in the box. Add the column times the number in the box. Add the column times the number in the box. Add the column times the number in the box. 10 plus negative 10 is no remainder. So the square root of 5 is indeed a solution. I also know that I know that irrational numbers come in pairs. So if the square root of 5 is going to be a solution, I also know that the negative square root of 5 is also going to be a solution. So I'm going to put that in the box and do synthetic division again. When I complete that process, I end up with no remainder, which is excellent. So those are two of my solutions. But where are the other two? They don't cross the x-axis. The other two are going to be imaginary. So how do you get those imaginary numbers? You peel the quadratic that's left over. In this case, it's x squared plus 0x plus 2. And you just need to solve that quadratic. You can solve it by either directly algebraically, which is not that bad. Just subtract 2 from both sides and take the square root. We're taking the square root of a negative 2, so that means you're going to have I times the square root of 2. So those are my two solutions. Positive I root 2, negative I root 2, square root of 5, negative square root of 5. All right, question number 2. Let's start by graphing that as well. All right, this guy is going to have the same kind of shape. It's also quartic. If you want to see the bottom, you can make the y minimum go even lower. There you go. And I'm looking for crossing points. This time it looks like they are crossing through integers. It looks like it's crossing at negative 3 and positive 3. I don't care which number you do, just grab one of those, like positive 3, and do the synthetic division thing. If you're right about that crossing point, then you'll end up with no remainder. Perfect. It also looks like negative 3 is a solution, so I'm going to put negative 3 in the box and do synthetic division again. I'm slowly knocking this fourth degree polynomial down by a degree. So when I get no remainder after the second round, now the resulting set of coefficients, that's the quadratic. Those are the coefficients of the quadratic that will give me my final two solutions. So again, solve this equation. You can use the quadratic formula if you want, or you can just solve it directly. X squared minus x squared equals negative 5. So again, I'm taking the square root of a negative number, and I get I root 5. So my four solutions, 3, negative 3, I root 5, and negative I root 5. All right, problem number 3. Problem number 3 is a cubic equation. So when I graph this guy, I only need to find 3 solutions because it's cubic. And if I zoom in a little bit, yeah, it looks like all 3 are going to be real numbers because I can see that the graph is crossing the x-axis 3 times. It looks like it's crossing down there at looks like negative 6, maybe negative 1, and 0. You can grab any one of those numbers you want and prove that they are, in fact, solutions. So maybe I'm just going to grab, maybe I'll start with the -6. Do synthetic division and show me that there's no remainder. The 1 comes down, the 1 comes down, times the number in the box, add the column, times the number in the box, add the column, times the number in the box, add the column, and I get no remainder. Perfect. -6 is, in fact, a solution. Again, you can do synthetic division 2 more times if you want to, but usually at this point, the result is a quadratic. Just solve that quadratic. X squared plus x plus 0 equals 0. I know I said there is no factoring, but it'd be so easy if you just noticed that there was an x was a common factor there. Each one of those parentheses, each one of those factors is going to give you a solution. So what makes x equal 0? 0. What makes x plus 1 equal 0? -1. So there's your 3 solutions. -6, 0, and -1. Perfect. Number 4. All right, when I graph number 4, let me get the equation up there. Let's turn that one off, this one on. All right, it's also a cubic, and I'm seeing that the graph is crossing the x-axis 3 times. That's great. All 3 solutions are going to be real numbers. And it looks like maybe -4 is a solution, -2 and +4. Go in any order you want. I'm going to start with -4 and do synthetic division and show that that is actually a solution. And let's see, 8 times 4, 32. No remainder is perfect. So -4 is one of my solutions. Again, you can throw -2 in the box, do synthetic division again if you'd like to. But at this point, I just bail out, look at the quadratic, and try and find the values that will solve that quadratic. You can factor that, but if you don't want to, you can use the quadratic formula. -b plus or minus square root b squared minus 4ac all over 2a. When you simplify all that, let me go over here to my calculator. What's underneath the discriminant there? 4 minus 4 times 1 times -8, that's 36. So we're talking about 2 plus or minus the square root of 36 over 2, which is 2 plus or minus 6 over 2. And if you do 2 plus 6 and then divide by 2, you get 4. If you do 2 minus 6, then divide by 2, you get -2. And there are your 3 solutions. -2, 4, and -4. Which is exactly what the graph is suggesting to us. Number 5. This one is a quartic equation, so there's 4 numbers defined here. Something special is happening at one of those solutions. Do you see how the graph doesn't cross through? Oh, actually, hold on, let me zoom in a little bit so you can see what's going on. All right. So do you see what's going on there at -1? There's going to be a multiplicity there. -1 isn't going to be just one of our solutions. The number -1 is going to count as 2 of our solutions. There's a multiplicity of 2 right there. I know that because the graph isn't getting cut. It's not cutting through the x-axis. It's just touching the x-axis and kind of curve bending away from it. So, I'm going to start with -1. You can start at any one of those crossing points you want, but I might as well go ahead and start with the -1 since that's going to where my multiplicity is. Do the synthetic division thing. Hopefully we'll end up with no remainder here in a minute. -24 plus 13 is 11. Let's see. Then I'm going to multiply by the number in the box, and I get no remainder. Perfect. But because of the multiplicity there, -1 is a solution. I can use -1 a second time. -1 is actually going to count for 2 of my 4 solutions. So watch, put -1 in the box a second time. And again, you'll see that there's no remainder. So not only did the number -1 work once, it actually worked twice. Now the result is going to be a quadratic, and just throw those numbers into the quadratic formula. So -b plus or minus square root b squared minus 4ac all over 2a. I need help with my calculator because I don't know what 16 squared is. But I'm going to subtract 4 minus 3 times 5. All right, that's the number 196. So we're talking about 16 plus or minus the square root of 196 over 6. The square root of 196, well, that's just the number 14, which is great. So we're talking about 16 plus or minus 14 over 6. If you do 16 plus 14 and then divide by 6, that's 30 over 6, which is 5. And if you do 16 minus 14, 2 divided by 6 is 1/3. So my 4 solutions are 5, 1/3, -1, and then -1 again. All right, and then for the 6th question, let me start by graphing that. All right, it's a cubic, and I'm seeing 3 crossing points. No multiplicities or anything weird like that. I just need to find those 3 crossing points. One of them is absolutely at an integer crossing point. All right, the other 2 maybe look like decimals, but -5 looks like a solid integer solution. So let me start with -5, do the synthetic division thing, and with any luck, I'll end up with, yep, no remainder. Take a look at those coefficients down at the bottom. That is a quadratic, 2x squared minus 4x minus 8. Solve that with the quadratic formula. Your second and third solutions will just come from that. -b plus or minus square root b squared minus 4ac all over 2a. Let me get my calculator to tell me what the discriminant is. 16 minus 4 times 2 times -8. That is 4 plus or minus the square root of 80 over 4. Now the square root of 80, that actually simplifies. 80 is made up of 2 times 40, which is 2 times 20, which is 2 times 10, which is 2 times 5. So 80 is actually made up of like a whole bunch of 2's and then a 5. In fact, 2 pairs of 2's and a 5. So if I simplify that square root, the square root of 80 is actually 4 root 5. And then since all of those things have 4 as a part of them, I can do 4 over 4, which is 1, and then 4 root 5 over 4, which is the 4's cancel out, and you're left with 1 plus or minus the square root of 5. So those are your 3 solutions. On to the back. All right, on to the back. So now we're going to have to deal with all this vocabulary. But in order to see what I'm looking at, I'm going to need to graph that equation. So I throw that into my calculator, graphing it. I'm actually going to make my window go a little lower and a little higher so I can see the where the top and bottom of this thing are. Oops, hold on. Go ahead and, oh, I gotta make that -60. Got it. All right, there we go. So we got a nice quartic looking equation. I'm going to use my calculator to find all of the critical points. I'm going to try and find those minimums, those maximums, and those x-axis crossing points. The x-axis crossing points are actually pretty easy to get. That one's at -4. This one's at -1. The next crossing point is at 1. And then the 4th crossing point is at 3. So those are my 4 zeros. I'm also going to need to grab the minimum and maximums. So let me go take a minute and go calculate the minimum value down here, the minimum of that chunk. My calculator tells me that that minimum is -2.94, comma, -48.13. All right, I got another minimum to find, so let me use my calculator to find that minimum. All right, that second minimum is 2.22, comma, -19.06. Those values are coming straight off of my calculator. There's also a maximum, a local maximum. Let me go ahead and grab that. My calculator tells me that that maximum is at -0.04, comma, 12.02. All right, so that's everything we're going to need in order to answer all of these questions. All right, so domain. Domain for polynomials is easy. It's all real numbers. It's everything from -infinity to +infinity. Done. All right, what about the range? When I'm looking at this graph, you might notice that this graph doesn't go any lower than that y value. What is that y value? Well, it's -48.13. So I'm going to write my range as bracket -48.13, comma, infinity. So it's everything from -48.13 and up. For the relative maximum, there's only one relative maximum. It's that little point in the middle. That location, my calculator told me, was negative 0.04, comma 12.02. What about the absolute minimum? There are two minimums here, but one of them is the most minimum. That one that is lowest is called the absolute minimum. And we already saw that that was, the coordinate of that minimum is negative 2.94, negative 48.13. All right, intervals of increase. That is, when is this graph heading uphill? So here's a section that goes uphill, and here's a section that goes uphill. There's two increasing sections, which I've just drawn in green. So tell me where the graph is increasing. We have that first bit of increase from negative 2.94 to negative 0.04. That's that section. But then I have another chunk of green uphill that goes from 2.22 all the way up to infinity. So there's two regions, and I'm just joining them together with a union symbol. Intervals of decrease, that would be everywhere else. So basically the places where the graph is going downhill. I'm seeing that it's decreasing all the way down from negative infinity down to negative 2.94. Then it goes up for a little bit, but then it's decreasing again from negative 0.04 to 2.22. Positive intervals. That is, where is the graph positive? So I'm just going to grab this sticky note and cover up the negative part, and let's look at the three places where the graph is positive. You have one chunk of positiveness everywhere between negative infinity and negative 4. Then you have this little like peaky bit in the middle. That goes from negative 1 to 1. And then anything beyond 3, so from 3 to infinity, that's increasing. Decreasing, negative intervals, that's everywhere below the y-axis. So it looks like there's two kind of U-shaped things. We just need to write those coordinates, or that range. So the first one is, it's negative between negative 4 and negative 1. The second one is negative between 1 and 3. All right, and then for this last problem, we want to see, is the leading coefficient positive or negative? I see that this graph is ultimately heading uphill, so it's got a positive leading coefficient. Is the degree odd or even? I know that graphs that start low and end high have odd degrees. Is the function odd? Does it have odd symmetry? Is it symmetric about the origin? No. Is it symmetric about the y-axis? No. So that means it has neither kind of symmetry. So it is neither odd nor even. And then if I count the straight line-ish pieces, that tells me that there's 5 pieces. It's 5th degree, which jives with the idea that it's an odd degree. And that concludes this.